Hi, my name is Lauren Mason, and this is my statistics project. The article I chose was called We Watched 906 Foul Balls to Find Out Where the Most Dangerous Ones Land, and this article was written by Annette Choi. So, first I'll summarize the article. So, as we know in baseball, it's very easy for audience members to be injured by, the balls flying all over the place. And so, the people who did the research in this article wanted to find out what the most dangerous areas of baseball stadiums were. First, they tried to find out the 10 baseball stadiums that produced the most foul balls, and then they went further and analyzed the data to find out what were the most foul-heavy game days from each of those stadiums. And then they decided to split the stadiums into a relative 7 zones. Here's a visual aid to help visualize, what zones these were split in and what it would look like. So zone one is behind the plate, home plate. Zones 2 and 3 are obviously right next to it, and it goes from the plate to the end of the dugout on each side, the team dugout. So, zones 1 through 3 are all netted in every stadium. That's the netting standard. You have to have nets from zones 1 to 2 and 3. Zones 4 and 5 are past the dugout. It goes from the dugout to the foul pole, and these are normally open. There are some stadiums that have netting there, but not all the way across. But in most stadiums, it is unprotected. And then zones 6 and 7 are the areas past the foul pole, just to the rest of the field. It's worth noting, I think, that most balls that land in zone 6 and 7 aren't really dangerous because they're so far, and there's not very many seats there, and it's so far, so they're not dangerous. So in doing this research, they found that an almost equal number of balls landed in the netted zones versus the non-netted zones. So in zones 1 through 3, 454 balls landed there, and 452 balls landed in the non-netted zones, which is zones 4 through 7. So I think you can see that there's not really that much of a difference in where the balls land. Next, they decided to measure the exit velocities of 580 out of the 906 balls. Well, I should say rather that they were able to measure the exit velocities of 580. Not that they chose 580, but that's what they could get. And it is worth noting that most of the most dangerous balls have higher exit velocities because they're going a lot faster, and it gives the audience less time to react, so they're more dangerous automatically. And it was found that the hardest hit balls landed in the unprotected zones. And so that combo, obviously just makes things a whole lot worse. You have the fastest balls going in the zones where there's no protection. This is a specific statistic that was found in the article. 71.8% of fly balls with an exit velocity of 90 or greater miles per hour landed in zones 4 and 5, which are unprotected in most stadiums. I do think it's worth noting that the balls that were landing in zones 1 and 3 were mostly missing exit velocities. They couldn't figure out the exit velocities for those balls, so obviously we don't know if those balls had high exit velocities because it wasn't able to be found out. So this brings me to the question. This is the question that is not addressed in the article that I came up with from the data. I have to admit, I did have some help, but I ended up choosing this question because it made sense. So the question is, are the exit velocities of the balls hit to the left different from the balls hit to the right? And if you can remember the visual aid that I gave, the balls hit to the left are zones 2, 4, and 6. And the balls hit to the right would be in zones 3, 5, and 7. We're not counting zone 1, because it's in the middle. So these are the descriptive statistics in zones 2, 4, and 6. So what I did is I took the data and I added up all of the exit velocities in each zone. So all of the exit velocities of balls that landed in zone 2, and all of the ones that landed in zone 4, and all the ones that landed in zone 6. And those were my those were my values in my data set. So in zones 2, 4, and 6 in the left, the n was 3, the mean, the x bar, the mean, was 596.1, and the standard deviation was 591.651. In the right, the n was also 3. The mean, or the x bar, was 585.033, and the standard deviation was 480.246. The null, so then I had to do a t-test to figure out everything else to solve the problem. I had to do a t-test. So the null hypothesis was mu1 equals mu2. The alternative hypothesis was mu1 is not equal to mu2, because in my question, I just said, are the exit velocities of the ones to the left different from the ones hit to the right? So my alternative hypothesis is mu1 is not equal to mu2, or is different than mu2. The test statistic, after doing the test, my test statistic came out to 0.0252, and the p-value was 0.9822. With this information, with this information and alpha being 0.05, it's clear that p was greater than alpha, and with this decision, we fail to reject the null hypothesis. And with this decision, we can interpret that there is not enough evidence to conclude that the exit velocities of baseballs hit to the left are different than balls hit to the right. And this is the chart I have of the means of each of my data sets, zones 2, 4, and 6, and zones 3, 5, and 7. And that's the end of my presentation. Thank you.